This article deals with the demand response (DR) application on refrigeration equipment for the hotel sector, establishing strategies at various levels of aggressiveness considering the thermal comfort in the facilities. The simulations are based on DRQAT software adapted to the Brazilian scenario. The analysis consists in a comparison of the results obtained with the electricity price in the short-term market in order to obtain an estimate of profits from DR. Besides establishing a relation between the value of DR per period of application and levels of thermal comfort. In this way, the circumstances in which DR becomes viable for the hotel sector are verified. The result of this analysis indicates that in order to provide opportunities for supplying drive with maximum efficiency of use of the resource, it is necessary to create mechanisms for load aggregation. Thus, the added flexibility becomes significant in both economic and energy terms. In order to present such analysis, Section 1 have introduction of the problem aborted in this article. Section 2 introduces the initial concepts pertaining to the subject and describes the software used in the simulations. Section 3 presents the applied case, the characteristics and the limitations for the elaboration of the strategies applied on the selected hotel enterprise. Section 4 explains those strategies and their application in the software. Section 5 shows the results relating thermal comfort, energy savings and profit simulation, followed by the conclusion in Section 6. Demand response (DR) is a new subject in the Brazilian electrical system. With the launching of the National System Operator ON's demand response pilot project, many speculations have arisen about the viability of DR in the Brazilian scenario. The regulation for the implementation of this modality in the balancing market is underway and the operationalization is still quite complex, as there are currently no practical cases for an application. Therefore, this case study aims at analyzing the opportunities and limitations for DR participation of refrigeration systems in Brazil, considering energy, climatic, physical and financial factors that may influence this result, based on the real data of a hotel business and the routine of its facilities usage. DR strategies were developed considering the levels of thermal comfort. The free software DRQAT, Demand Response Quick Assessment Tool, developed and made available by Berkeley Lab, was adapted to the Brazilian climatic conditions and used to analyze the relations between temperature variation and energy consumption. The main objectives of this study are to allow the implementation and replication of DR strategies and to verify the economic feasibility of them. The DR of HVAC equipment has a greater chance of adhering to the pilot project since it does not considerably affect the productive process of a participant. HVAC systems are a very relevant resource for dispatching and response actions of the demand of commercial buildings because they have great representability in their total electric load. In addition, the possibility of having thermal storage in the internal rooms allows the temporary shutdown of the air conditioning systems without immediate impact to the occupants. In commercial ventures, it is common to have the automation of HVAC systems with centralized temperature control, which is essential for the provision of a reliable response. The use of automation eliminates the need for interaction with a resource operator when a demand response event occurs. The Demand Response Quick Assessment Tool (DRQAT) software is a free tool developed and made available by Berkeley Lab. This software assists the analysis of DR event strategies for HVAC equipment, considering the load curve, equipment capacity, peak hours of the energy utility, internal ambient temperatures, weather data, building types, and location. The software uses North American weather data and, therefore, some adaptations in its data files were necessary for the simulations to be compatible with Brazilian scenario. For this purpose, after a study of the software's inputs and outputs and with the authorization of the DRQAT software developers, the climate files and the locations of the climatic zones were changed, adapting the software to the Brazilian conditions. The software used in the analysis presents the thermal comfort graphs, and it is possible to verify the consequences of the adopted strategies. The measurement of the thermal comfort of the environment uses indexes such as predicted % of dissatisfied (PPD) and predicted mean vote (PMV), with the purpose of characterizing the user's thermal sensation. The PMV is an index that indicates the satisfaction and dissatisfaction of the environment in the 7th scale, classifying the thermal discomfort by low or high temperature. PPD is an index that, related to PMV, indicates the percentage of people thermally dissatisfied with the environment, varying the classification between very hot and very cold. That figure shows the variation curve of the PPD index as a function of the PMV. Thus, the premise is that the PMV index should not be more than 1.7 so that the number of people dissatisfied is no more than 50% during the DR event. A hotel complex in the city of Sao Paulo, Brazil was selected as a case study for DR strategies simulation and analysis. For this building, all the dependencies in which DR can be performed were analyzed as disaggregated loads, considering the operation hours and the number of people in each room, in order to maintain thermal comfort norms. The main common areas, such as restaurants, the gym, and the convention center, were considered. The apartments were not included in the simulation since it is not practical for a hotel complex to interfere with the individual thermal comfort of the accommodations, which temperature is controlled by the guests themselves. DR events were simulated via entering in DRQAT the climate data, the capacity of HVAC equipment, the operational hours of each room, the building dimensions, and the number of people in each room. Due to the business characteristics and the variation of its load during the seasons, the analysis considers two distinct periods, high season and low season, in the southern hemisphere. High season is defined by the months of July, December, January and February, and the low season by the remaining months. Among the DR strategies in HVAC equipment described in previous work referenced, the techniques listed in table were chosen because they are the most used in DR events already consolidated in other countries. Precisely because they present satisfactory results and do not require great sophistication of control in order to be applied. The schedules elaborated for DR events considering the peculiarities of the client, aiming to guarantee the standard thermal comfort. The techniques used were global temperature adjustment and passive thermal. 3 strategies were defined: conservative, average, and bold. These strategies differ according to the level of thermal comfort reached during the event, and even in the most audacious strategies, it is expected to consider the results of the PMV and PPD indexes in order to avoid excessive discomfort. The first strategy, based on the global temperature adjustment, is very conservative and consists in turning off the HVAC equipment at 6 p.m., increasing the temperature set point from 22 Celsius to 24 Celsius and the chilled water temperature from 7 Celsius to 9 Celsius. The duration of the DR event for this case is 1 hour, returning abruptly to the previous levels as soon as the established time ends. This is the schedule for strategy A. This is the air temperature point for strategy A. This is the chilled water temperature set point for strategy A. The second strategy differs from the previous one by using thermal passive simultaneously with global temperature adjustment to force the DR event to take place in 1 hour, from 6 p.m. to 7 p.m. The temperature set point was gradually increased from 5 p.m. The equipment was then switched off at 6 p.m. and turned back on at 7 p.m., gradually decreasing the temperature until it reaches the values prior to the event. The temperature variation should be, as well as in the previous strategy, of 2 Celsius, both for the air and for the cold water. This is the schedule for strategy B. This is the air temperature set point for strategy B. This is the chilled water temperature set point for strategy B. This strategy aims to leverage DR by turning off the chiller at 8 p.m. and keeping it off, increasing the temperature to 24 degrees Celsius. The DR will take place from 8 p.m. to 9 p.m. This is the schedule for strategy C. This is the air temperature point for strategy C. This is the chilled water temperature set point for strategy C. After applying the aforementioned strategies, the program issues a report that contains energy values and thermal comfort. This section presents the analysis of the compiled results. For each strategy, there's a graph of thermal comfort, where it is possible to observe the variation of the PMV index throughout the day. For a better comparison of the strategies, the figure shows the overlap of graphs in the same hot day of the year. In all the adopted strategies, the thermal comfort did not show great alterations, having reached a maximum point of 1.25, which means a sensation of slightly warm. Hence, there is scope to implement bolder strategies than the ones developed in this work. The results in figure shows that strategy B is the most effective for reducing the load. This strategy still ensures that the load does not increase in the previous moment of the realization of the DR, avoiding more energy expenditure in the total accounting. On hotter days, the electric charge is higher due to the higher demand of the refrigeration equipment, and this has a relation with the relevance of DR events in those days. In this way, the 10 hottest days are presented in the following graph, which brings a mean of the results in energy delivered accumulated by the simulated environments for each strategy. The values correspond to a DR event of 1 hour. The values obtained, summing up the 3 simulated areas in the hotel, reach a maximum of 25.2 kilowatt-hours in Strategy B, which represents almost the total load coming from the restaurants in the convention center. The results generated are in accordance with other simulations using the same software as presented and referenced where for enterprises of similar area. The 1-hour demand response period presents approximate values of energy savings. In order to establish a relationship between the price in Brazilian money per megawatt hour asked by a DR bidder and the number of events that would be called by that price, it is possible to simulate operations in the short-term market and verify their viability. The following premises are considered. Maximum activation of 1H on days in which the PLD is higher than the price demanded by the consumer, and the DR event would be carried out at the peak hours of the PLD to maximize the profit obtained. The Brazilian electric system is divided into 4 sub-markets: south, southeast, northeast and north. Each of them concentrates regions of the country where energy circulates freely. The line dividing each submarket is determined by the exchange limits present in the transmission system, that is, electrical constraints in the energy flow between the different regions of the country. Each submarket has a specific energy price. In Brazil, this energy price is called Difference Settlement Price, PLD, and currently the PLD is set weekly, but the hourly PLD is being tested. In Brazil, the hourly Difference Settlement Price, PLD, schedule is being tested and will be implemented in 2020. Making it possible to carry out transactions through the variation of prices during the day. Considering the PLD values of the last month of December, it is possible to establish, during the monthly period, the periods in which the DR would be requested. The figure relates pricing levels and shadow PLD data in December 2018. For all submarkets, establishing a generic function. Analyzing the peaks of the graph in the previous figure and following the assumptions adopted. The amount of DR events that would be triggered is estimated as a function of the price charged by the consumer to make their load more flexible. This figure lists the DR pricing and the number of events that would be called into action according to their pricing levels. Applying the results obtained in the hotel sector, the individual gains are not significant to the point of justifying participation in DR events. However, if other hotel developments in the city of São Paulo are considered and their loads are virtually aggregated, interesting results are obtained. For this purpose, 5 more hotels in the city of São Paulo were selected. Through the replication of the previously explained simulation for the 5 other developments considering the relation between total demand and the decrease of load, it is possible to obtain an approximate aggregated value for DR for hotel sector in São Paulo. Considering that all projects are aggregated in the same pricing for DR activation, the aggregate monthly value for 1 hour of DR is obtained on all days in which the PLD price is higher than the specified price level for the southeast submarket. The table shows these results, considering the aggregated DR estimate of 125.3 kilowatt-hours. These values represent only the revenues obtained from short-term market transactions, and it is necessary to subtract the value of the energy contract that the consumer already owns. According to the analysis, despite the load aggregation effort, revenues obtained from participation in DR events are still not attractive from the economic point of view for participation in the energy market. Considering the results obtained, the DR of HVAC equipment, considering DR for sale in the energy market, it is not yet economically viable in the current scenario in Brazil, since the profitability generated by the participation in such events is not sufficiently significant to the consumer. However, with the evolution of other markets in Brazil, such as capacity and balancing markets, the DR of these types of equipment becomes more attractive. With the evolution of these markets, this type of program no longer has a purely economic bias on the part of the consumer and becomes a product of security and reliability of the system, having its value measured not only by the energy saved but by the disconnected load. In addition, this work allowed the research team to conclude that in order to provide opportunities for DR supply, an essential resource to make energy use more efficient, it is necessary to create load aggregation mechanisms so that added flexibility becomes significant both in terms of energy and economy.